Hi all, let's take a look at our last topic for the semester, the dot product. This is going to be a pretty easy section, in fact. We're going to be finding the dot product between two vectors, and then we'll use that dot product to find the angle between two vectors. Use the dot product to determine if two vectors are orthogonal. Orthogonal is another word for perpendicular. Whenever we have vectors that meet at a 90-degree angle, we don't call them perpendicular, we call them orthogonal, but it means the same thing. Find the projection of a vector onto another vector. Express a vector as the sum of two orthogonal vectors and compute work. Okay, so up first, the dot product of two vectors. In the previous section, we learned that whenever we had vector addition or scalar multiplication of a vector, the end result was still a vector. The dot product of two vectors is going to end up in a scalar, some real number value. It's not going to be a vector. Now, whenever we do a dot product, let's say we have vector v that's some coefficient a sub 1 times I plus b sub 1 times j, and another vector w that's a sub 2I plus b sub 2j. Now, the dot product, all it's going to do is it's going to take the coefficients of the horizontal component I and multiply them together, add that product to b1 times b2, or the coefficients of the vertical component multiplied together. So it's the product of the coefficients of the horizontal component plus the product of the coefficients of the horizontal component. The dot product of two vectors is the sum of their products of the horizontal component and their vertical components. So these problems are going to be pretty straightforward. Notice if I have vector v is 7i minus 4j and w is 2i minus j, I ask you to find the dot product of v and w. You say, well, okay. Then I would multiply their horizontal components, 7 times 2, add that to the product of their vertical components. That's going to be negative 4 and negative 1. Well, I get 14. This will be plus 4 for a total of 18. Now, one thing I want to point out is that whenever we have the dot product, it doesn't matter in which order the dot product is taken. V dot W, same thing as W dot V. If you think W dot V, J, well, it's just 2 times 7 plus negative 1 times 4. Since order of multiplication is irrelevant in here, then the dot product in either direction is going to yield an 18. Any dot product is the same no matter what the order is. Now, can you take a vector dot product with itself? Of course. You would just multiply the horizontal components or square the horizontal components and then add that to the square of the vertical components. So I would say 2 times 2 plus negative 1 times negative 1 gives me 4 plus 1. W dot W would be 5 in this case. Now, properties of dot products. The first property is what I tried to show on the previous page, is that the order of the dot product does not matter. U dot V is always equal to V dot U. What if I take a vector U and multiply it by the sum of vectors V plus W? Well, then that U really could be distributed through that sum, and you could say, well, I could take the dot product of U times V and add that to the dot product of U times W. Most time, even though you could do that, most of the time it will be more efficient and easier to go ahead and sum the two vectors on the inside and then take the dot product. So as far as efficiency of problem, the first way is probably the quicker way, but this is still going to give you an equivalent answer. Now, what if you have the zero vector? Well, the zero vector times any vector v, it's going to give you a 0. And then what if I take a vector dot product with itself? Now, this I didn't mention on the last page, though we could have. The dot product of any vector with itself is going to be the square of the magnitude of that vector. Please notice if I go back one page here, I said W dot W. Now, if I ask you to find the magnitude of W, you just said, okay. it's the square root of 2 squared plus -1 squared, all under the square root. And you said, well, that's going to be 2 plus 1. That's the square root of 5. Well, notice the answer we get for w dot w. We get a 5, which is nothing more than the square of the magnitude of w. So I can say, okay, that's pretty useful information. The dot product, if a vector has a dot product with itself, it's nothing more than the square of the magnitude of that vector. If I have some scalar multiple of c times a vector u, that's being part of a dot product with vector v, then I could go ahead and factor that c out, go ahead and take the dot product and then multiply it by c. Or I could say it doesn't matter which vector is multiplied by c. I could leave vector u here and multiply the scalar multiple times v and then take the dot product. Any of those processes are going to give us the exact same answer. Now, an alternative format for the dot product, and this actually helps us find the angle between the vectors. So I can say the dot product of v times w, it's the magnitude of v times the magnitude of w times the cosine of the acute angle between them. So whenever we have two vectors, of course, there's always going to be an angle. Take the smaller angle and make sure you call it a positive angle for this angle theta. It says where theta is the smallest non-negative angle between them. Now, the next thing you can think of as kind of a corollary to this theorem here is that think about what if these vectors are orthogonal, meaning they cross at a right angle. Well, you know if they cross at a right angle, then theta is 90 degrees, and you know the cosine of 90 degrees is 0. So one of the things that we're going to be able to do with this formula right here is say, well, anytime the dot product is 0, that is evidence that these two vectors are orthogonal to one another. There's no other way that the dot product would be 0 except for the fact that the two vectors must meet at a right angle. Now, if I wanted to solve for the cosine of theta in this last formula, all you would do is divide by the magnitude of v and divide by the magnitude of w, and you get the cosine of w is equal to the dot product of v times w over the magnitude of v and the magnitude of w. And thus, we can also say theta is equal to the inverse cosine of the dot product divided by the product of the magnitudes. Now, let's look at an example with that. So in this example, I give you vector v, that's 4i minus 3j, and vector w, that's I plus 2j. And we're supposed to find the angle between them to the nearest tenth of a degree. No problem. I know that the cosine of theta should be the dot product divided by the product of the magnitudes. The dot product of u times v, that's, v times w. We put our vector w, we'll take the dot product with vector w here, which is I plus 2j. And then we'll divide that by the magnitudes here. I know the magnitude of v is just going to be the square root of the horizontal component squared plus the vertical component squared. So that's the square root of 4 squared plus 3 squared. The magnitude of w is going to be the square root of 1 squared plus 2 squared. So now when I simplify this, the dot product, you always multiply the coefficients of the horizontal components, so 4 times 1, add that to the product of the vertical components, -3 times 2. So my numerator, it's going to end up being 4 plus a -6 for a -2. My denominator, the first square root's the square root of 25, which I could have went ahead and called 5 on the root of 5. The second one, of course, is the root of 5. I chose to go ahead and multiply these out and just call it the square root of 125. I could have left it 5 on the root of 5 in that denominator. Doesn't matter because the goal in this problem is to solve for theta. Theta is going to be the inverse cosine of this fraction. And the nice thing about dealing with inverse cosine is we always want the angle theta, the smaller angle theta. Well, the smaller angle theta is always going to be an angle between 0 and 180 degrees anyway. Well, look what the domain of the cosine is and such that the inverse cosine exists, 0 to 180 degrees. So you never ever have to worry about the answer that you get whenever you're taking the inverse cosine here. It's always going to give you the accurate answer. You don't have to think about what quadrant it's in or anything like that. It will always be accurate, which is a wonderful relief compared to other problems. Now, when we talk about parallel and orthogonal vectors, we say two vectors are parallel when the angle theta between the vectors is 0 or 180 degrees. Now, obviously, if it's 0 degrees, the vectors are pointing in the exact same direction. So if I have a vector v and a vector w that have a 0 degree between them, it's because they're going in the exact same direction. They may just be multiples of one another. So if I have vector v is the vector I plus j, and vector w is the vector 5i plus 5j. They're going in the exact same direction. W is just larger than v. They would have an angle of 0 between them. Now, if the angle is 180, that just means they're going in opposite directions. That might be like if vector v is negative I minus j, and vector w is 2i plus 2j. They go in opposite directions, but they still are all on the same line at that same angle, at least. It's just one's going to the right and one's going to the left in this case, that have an angle of 180 degrees between them. Now, orthogonal vectors, it's when they meet at a right angle. And the nice thing about that is that the dot product will be 0, showing us that the two vectors are orthogonal. Remember, again, it's because the cosine of 90-degree angle is 0. So whenever you take the dot product and you say it's just the magnitude of the two vectors times the cosine of the angle between them, boom, dot product will be 0 when the vectors are orthogonal. Now, notice my next example, determining whether vectors are orthogonal. You'd say, well, okay, all I have to do, just like you just said, is take the dot product, which is going to be the product of the horizontal components, 2 times 6, plus the product of the coefficients of the vertical components, 3 times negative 4. Well, 2 times 6 gives me 12, 3 times negative 4 gives me negative 12. So when I add these two together, I get a 0. Dot product is 0, so I am 100% confident that vector v and vector w meet at a 90-degree angle. Now, could you graph these out and show that the angle between them is 90 degrees? Sure, you could. There's no need to do that, though. These vectors are orthogonal. Now, the vector projection of v onto w. If v and w are two non-zero vectors, the vector projection of v onto w is, the notation for it is, we say the projection of v onto w. It's equal to the dot product of v and w divided by the magnitude of w, quantity squared, and that's going to give you a scalar. You take that scalar and multiply it by vector w, and it's going to be the projection of vector v onto w. Now, you'll see down here at the bottom of the page, because I thought you might be thinking, why in the world would we need to know this? These vector projections are useful in physics applications involving force and work. Let's say that you're trying to pull a box across the floor, where your floor is this vector w down here, and you're trying to determine the amount of work done. Well, whenever you're pulling that box, if the force vector v here is at an angle, then quite a bit of the force that you're exerting is going to be wasted due to the angle that you're pulling it at. If you were pulling it at the same direction of vector w, you'd say, well, everything is going to go into the pull. But if I'm pulling at an angle, quite a bit of that's going to be wasted in an upward direction versus the whole horizontal direction. So we talk about these vector projections in work problems. So in real life, this the upward pull might be useful to reduce the friction, but if we're thinking of it just simply in terms of physics problems terminology, the energy would be inefficiently wasted for the horizontal movement of the box. It's not going to move it horizontally perfectly. So whenever we talk about the vector projection of V onto W. All it does is it results in you're going to drop a perpendicular down to W, and the projection of V onto W is going to be you can think of it as kind of like the shadow of V on W. It's not the full length of V. If I pulled V down here to W, it would be longer than that, but it's going to be, if you take the very tip end of V, pull it down and say, well, that's going to be the resultant factor on W. That's also going to be your force vector in that direction of W that we have from pulling V at an angle of theta. Now keep in mind, the greater that angle theta is, the less that projection of V onto W would be. What if I drew theta more steep here? Like instead of, I drew it pretty much at a 45-degree angle. What if I drew it at a 60-degree angle? Even if V is still the exact same length, its projection on W would be less. And you can see, ooh, well, what if V is at a 90-degree angle from W? It's not going to have any projection on W whatsoever. So that would be like, what if you tried to pick a box straight up? Well, that's not going to help move it to the left or right. So you just say, well, if you're picking it straight up and not having any horizontal movement, you're not creating any work. So in order for the work to exist, in order for the box to be moved, you're going to have to pull it at an angle that's not just a 90-degree angle. It's going to have some horizontal movement. Now, let's take a look at that. If we find the vector projection of one vector onto another, let's say I'm looking at the problem where I have vector V is 2i minus 5j, vector W is I minus j. I want to find the vector projection of V onto W. So this is called the projection of V onto W. You don't have to draw the little arrows if you don't want, though technically they're supposed to be there. We say, all right, we know how to do this. It's the dot product of V and W divided by the magnitude of W squared times vector W. We know all of this portion is going to give us a scalar. Then we'll multiply that scalar by the vector W to ensure that all of this force is going in the direction of vector W. So I can say, okay, the dot product here, I'm going to take vector 2i minus 5j and have the dot product with vector I minus j. All of that's divided by the magnitude of W squared. Well, the magnitude automatically is the square root of the horizontal component squared plus the vertical component squared. So that's 1 squared plus a negative 1 squared. And so then I can say, well, all of that's just going to give me 1 plus 1. That's the square root of 2. Well, that square root of 2 is going to go away in the next step because I'm squaring that magnitude. The square root of 2 squared is just going to become a denominator of 2. Now, as far as my numerator goes, it was the dot product. So I said, well, that's going to be 2 times 1 plus negative 5 times negative 1. That gives me 2 plus 5 for a numerator of 7. So I'm thinking of this, well, this is going to be 7 over 2 times vector W. That's what I have down here. So I know that the projection of vector V onto vector W it's going to give you 7 over 2 times vector W. So this vector was quite a bit larger than this vector, so its projection on vector W is really going to magnify what happens on vector W. So I can say, well, 7 over 2 times vector W is 7 over 2 times I minus j. And when I do that, I can say, well, that's just 7 over 2i minus 7 over 2j. So this is the projection of vector V on to vector W. Now, when we talk about these vector components, whenever we're doing these projections, and if we say that this vector, if we subtract the vector projection from the original vector V, what you're going to be left with is just the perpendicular distance vector from V to W. So the vector that you're left with is going to be orthogonal to the vector that you're the projection on V. That's what this next page is trying to say. Let vector v and w be two non-zero vectors. Vector v can be expressed as the sum of two orthogonal vectors, v1 and v2, where v1 is parallel to w and v2 is orthogonal to w. So if I say, let's let v1 be the projection of v onto w, which this is just my vector projection formula, then vector v2 is just going to be whatever your original vector was minus this projection. And so then I can say, well, then obviously v1 plus v2 would give me back the original vector v. So the vectors v1 and v2 are called vector components of v. So the first component is the projection of vector v going in another direction or another vector w's direction. And then the remaining vector is what's left over from v. So it's going to be the vertical movement, which is going to be orthogonal to that vector v1. And this process is called decomposing vector v into v1 and v2. Now, let's take a look at a problem like that. So we've already done the vector projection of v onto w, where v was 2i minus 5j and w was I minus j. So just to remind you, we've already found the projection of v onto w was 7 over 2i minus 7 over 2j. So if I allow the first v1 vector, that's a portion of the vector v, to equal this vector projection, 7 over 2i minus 7 over 2j, then I could say, well, then the remaining v2 vector is just the original vector v minus this vector. And whenever you say, okay, your original vector here minus the vector projection that we have to find, that we already did find, I can say, well, that's going to give me 2 minus 7 over 2i. When I do that, 2 is the same thing as 4 over 2i. 4 over 2i minus 7 over 2i is going to give me negative 3 over 2i. Then I have minus 5 minus a negative 7 over 2. This is the same thing as minus 10 over 2. Then I'll be adding 7 over 2. I'll get a negative 3 over 2j. Now, I know that this vector has to be orthogonal to the vector v1. Notice if you tried to take their dot product, you'd be saying 7 over 2 times negative 3 over 2, plus negative 7 over 2 times a negative 3 over 2. Those two products have opposite signs, but they'll have the exact same value. The value would be 21 over 4 and negative 21 over 4. So I can say their dot product was 0. Yes, they are orthogonal to one another. One's going to give you the vertical movement of v, the other gives you the horizontal movement of v. So you can say, hey, then v1 plus v2 together would represent v. We have decomposed v into its direction in terms of vector w plus the vertical part of vector v that w cannot account for. So I can say v1 and v2 together would equal vector v. Now, the definition of work. Work is just normally talked about as force times distance. And if we're talking about a vector that's moving some point A to point B, then we can say, well, the work is going to be the force times the length of that vector from A to B. When computing work, it's going to be easier if you think about it as the magnitude of the force times the magnitude of the vector here times the cosine of the angle theta. Let's look at an example of that. So this is similar to the projection problem I had earlier. It says a child pulls a wagon along a level ground by exerting a force of 20 pounds on the handle that makes an angle of 30 degrees with the horizontal. How much work is done by pulling the wagon 150 feet? Now, the important thing here is that the wagon is moving, so work is occurring. But one thing you need to think about is that work is not how much force is exerted. You could sit there and be pulling on this wagon with all of your might, And if that wagon's not moving, you're not doing any work. So the work is what's happening down here, not what's being exerted up here. So you say, well, how do I account for that? Well, I've got to find the horizontal, the work done on the horizontal. That's where the wagon is. In order to do that, I can say, well, okay, the work is going to equal the absolute value of, sorry, I should say the magnitude of the force vector. And you'd say, well, it's 20 pounds with the handle. And then times the distance it's being pulled. Well, it's being pulled 150 feet. Times the cosine of the angle between the force vector that you're pulling it at and how far it's needing to be pulled. Well, that's 30 degrees here. I know that the cosine of 30 degrees is going to be the square root of 3 over 2. I would be saying 20 times 150 times the square root of 3 over 2, and rounded to the nearest foot pound, you could say the work that's being done is approximately 2,598 pounds per foot, or foot pounds in this case. That's a common notation for work. You don't have to worry about the notation so much. We're just going to be working a few of the application problems within this section, and they all should appear pretty much like this, where you'll just say, we know it's going to be 20 pounds times a distance of 150 feet times the cosine of the angle. Of course, our unit is going to be in foot pounds because it's multiplying pounds by feet. Okay, guys, I will stop at that. Please take a look at my homework solutions if you have any trouble. And as always, let me know if you need any help.